Right, so I hope my slides are visible. So, let it appear. The net is very slow today for me. Yeah, all right. So, uh, okay, let's see if we can start now. Yeah, so today what we want to talk about is the convolution neural networks. So I hope all of you remember that last week we were talking about neural networks in general. We learned about what a neural network is and what it is made of, and so how does a neural network operate? What are perceptrons? How does backpropagate happen? So all those things we got introduced to, and in this week's lecture session, Sir has already taught about convolutional neural networks. So today's presentation, this session will be kind of based on convolution neural networks only. So it will be like why we require it, how it is to be applied, all those things we'll go through together. So the question that comes to mind is we were we were quite okay, like neural networks came into our lives, and we saw that it's a good way of learning from data. So I mean, why do we need to learn more then? What is there in neural network? I mean, the architecture that we saw last day, the kind of things that we saw last day, or probably in the last week, there was some what was the problem with that we need something new. So that is what we are going to learn today. So the problem is these whatever neural networks, 2 layer 3 layer neural networks that we saw last day, they are, while they are good to show you some experiments and all, they are not powerful enough to handle sophisticated data like image, text, and so on. Yeah, so that is why we have to deviate from that particular, the particular neural networks with hidden layers and all, and we have to move to something stronger. That is why we have come up with things like CNNs, RNNs, and all. So some architectures which are which have expertise in handling images, some other architecture may have expertise in handling text and so on. So coming to this convolutional neural network. So before going into it, let's have a try to have an idea of again why a traditional neural network may not work in the image space. So if you look at this cat image, right? So this cat image is, we all know that images are nothing but grids of pixels. So it's like a matrix or 2D array of pixels. And now what I've done here is I've taken a small patch of it here inside this entire big image. And this entire patch is actually represented by this big of a matrix, right? So there are so many numbers that basically represent this particular patch. So imagine that if this particular patch is so big, then if you take the entire image, how big that will be. So it's like, suppose image sizes can be, standard sizes are like 1024 cross 1024. Suppose this is a square image. So 1024 cross 1024, which means what? 2 to the power 10 into 2 to the power 10 once again, which is 2 to the power 20. Which means what? That a single image, basically, if you flatten it, it becomes a vector of dimension 2 to the power 20, which is huge basically. So so that is why, yeah, so that is why Yeah. So what we were saying is that a traditional neural network cannot process that large amount of or that large dimension of vectors, because we all have, compute. We all have, we want to fit our models into small resources, smaller computing resources. We do not have infinite resources. So that is why this is the problem with images, which is different from, other data, that it's very, very, very high dimensional. So the scale of the dimensionality is, I mean, it's too big. It just cannot fit into a traditional neural network. So that is why imagine. So that is why it says that, for a fully connected feed forward neural network that we saw last day, it's impossible to fit this much amount of data, where this small patch is so big basically. So that is why one thing that is why what we are trying to do is we are trying to do away with this fully connected concept. We do not want fully connected layers uh, inside the neural networks. We have to get smart, and we have to come up with something so that we do not require so many hidden connections and hidden neurons and so on, so that we can manage with a very less number of parameters, because you also have to the number of I mean you also have to learn the parameters in order to learn how to deal with this image. Either you have to classify, or you can do object detection or whatnot. But because of in doing that, you have to learn the weights also, and that is why the weights cannot be so big that you cannot learn them. And also note one thing, that the image is not simply just a 2D array of numbers, right? So the specific areas in the array, 2D array, have specific meanings. For example, this area of the dispatch in the 2D array basically represents your cat's head. This entire area represents your entire cat. This area probably represents the cat's body, right? Which means what? That in your image, in your matrix, basically specific areas mean specific things, right? And we do not want to, suppose we divide the image, we take this image and randomize the pixels, so that this eye goes somewhere, this eye goes somewhere, this ear goes somewhere, this ear goes somewhere, everything is randomized. So I mean we won't be able to make any meaning out of the image in that case. So that is why we want to process the image in such a way inside the neural network, that even though your first of all, we want to decrease the number of parameters, we want to somewhere control the high dimensionality of the data, and besides that we want to maintain these structures, we want to maintain these objects as it is, as whatever, in whatever shape they have come, we do not want to lose that. So that is the two, these are the basically two things that we have to remember about images. Okay. Yeah. So what we have talked about is nothing but this event called parameter explosion. So again, as I said, that you have an image you have an image like this, for instance, and suppose you have a fully connected neural network, which means what? That you will have these incoming data points, these will be your inputs, and these will be your hidden layers, hidden units, one by one. So just consider that, suppose this is a 200 cross 200 image. So basically, which means what? How many pixels are there? 40K, I think. Yeah. So here, suppose you have this particular neuron, right? So this is just one neuron. So in order to learn this, how many connections do you need? Just imagine. So from each of these pixels, you would need one parameter in order to learn this, right? So that will be itself equal to somewhere around 40K, because because connections are coming from each of these input values. And moreover, suppose, because this is so big, this cannot be small, this cannot just contain three hidden units. It might contain again somewhere comparable. So it might be again around 40K here. So each of these has 40K incoming connections, and here there are 40K units. So it's basically total number of parameters just for a single layer becomes 40K into 40K, which is kind of around 2 billion, right? So that is value, that is some value that we cannot even imagine. So that is the problem with a few traditional feed forward neural network. There's so much, it 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 leads to some an an explosion in the parameters. So it's so huge that you cannot even process it with your current computers and all. So, and moreover, as I said, that instead of, we do not need connections from, I mean, with respect to every input point that is there, every pixel that is there. What we need is, we need to maintain the spatial structure of the image, right? So that is also something that we have to take care of. Moreover, the more parameters that you have, as it says here, I mean, the more number of parameters that you have, in order to train them, you have to have okay, yeah, yeah, the more number of parameters you have to have more, that much amount of data in order to train those parameters. So that we are never going to have. So we'll never have that much data that can train this much amount of parameters. So that is why we need some control over the data, and we'll use the properties of images basically in order to get that control over the neural network. And one such property is that, as I said in this cat image, that we need to maintain the spatial structure of the cat. And our neural, our weight parameters that we learn, they should be meaningful enough so that they can, capture patterns from these, basically these different parts of the cat, the ear, the eyes, the nose, and so on. So we'll take advantage of this fact that we need to maintain the spatial, information in the image, and you'll see that how we come up with a technique that shortens the number of parameters but leads to good amount of learning. Right. So these are what a CNNs are. I mean, this is an entire kind of a convolutional neural network as we know of it. So there's an input image. Now, what you do is, instead of going for something like this, where one neuron is connected to each of the image pixels, what you do is, you do it area wise. So you pick up something called a patch from the input image, and you have a filter, a weight vector, which we call either filter or kernel, um, uh, in the neural network terms, where this filter is basically a collection of learnable parameters, and that filter is used to learn the connect, I mean, so what happens is that you convolve that particular filter with this particular patch, and you learn something in the in this part, which is called the activation map. So I mean, this means what, that you have a set of, so we'll show in some more details in the upcoming slides. So what you are trying to do is, this is the input point, this becomes one of your hidden neurons that we saw in the previous slide. So instead of having all these connections between, I mean, from this hidden layer to each of these pixel values, this becomes your neuron in the next stage, where it is only connected to this small patch in the this in the input space. So this neuron, this is a neuron, and it's not connected to every pixel in the image. It's only connected to a small pixel in the small amount of patch area in the image. Similarly, you might take this particular patch, maybe around the feet of the teddy bear, and that is again, this particular area is this is again a neuron, and you are not connected to the entire image. That neuron is not connected to the entire image, but it's only connected to the corresponding area in the uh, input image. So that is how we take advantage of the fact that we have to, we, I mean, not take advantage, but rather we want to maintain the spatial information in the image. And in order to do that, we have to, so what we do is, we connect corresponding areas in the, I mean, between the input image and the hidden neurons. So that is what is convolution about. So I'm sure this, a lot of it didn't mean anything to you at this point, but we'll look into some examples in the next slides. Okay.
Ma'am, a small
Yeah,
doubt,
yeah,
ma'am.
sure. Go on.
Can you go to previous slide?
Yeah.
Ma'am, the only reason of going to CNN is only because of parameter explosion. Because suppose we have supercomputer or some very big computer which can compute this 2 billion parameter,
Hmm.
then we should go for CNN or we should go for
No,
FF
you should,
and
yeah, you should still, so CNNs are still better because, so suppose you do something, suppose you have a huge supercomputer that still can do this kind of a processing, it still does not maintain your spatial relations. It still does not maintain that, there's an eye here, so the left eye is here, that means there will be a right eye here, and then there will be a nose somewhere below them, so that structure is not somewhere getting lost in this kind of an architecture. Whereas, suppose in this kind of a system where what you do is your so this entire whatever you are seeing, this is also again a collection of neurons. So here your there will be a certain neuron over here which will be only connected to this nose, and similarly the eyes and so on. So what will happen is here you while you are losing what I mean you are losing what is present at what location in the image. So again going back to the cat image, you are losing where its ears are, where its eyes are, and so on. So that is getting lost in a typical neural network architecture. So we'll see in CNNs how that gets maintained basically. So that is the most important motivation behind going for a CNN instead of a feed forward neural network. And also another motivation, as I just told you, is that say suppose we have a huge huge supercomputer which can still compute all of this, we'll never have enough data to train this much amount of parameters. So this is just the parameter for one hidden layer, this 2 billion. So we'll have to do complex tasks, we'll have many hidden layers, so all of them will have so many parameters. And to because deep learning systems are very data hungry, you have to give them lots of data to train them. That is why we cannot go with such a huge number of parameters that we cannot even train them. We do not even have enough data to train them. So that is kind of the motivation behind going for a CNN instead of a feed forward neural network. So again, it's like what kind of architecture you want to use depends on what kind of data you have. So like I said, images have this problem of maintaining the spatial information. Text will have some other problem. So that is why text has a separate class of architectures that people tend to use. So it's all like why these architectures came into existence is again because we needed them basically. We needed some way of figuring out that this is how a teddy bear looks like, where there its feet are below, its hands are somewhere on the side, its face is here, and so on. So in order to understand that, we needed something like CNNs. That is why we go on using CNNs. So the pipeline of CNN is something like this, that you have an input image and you have convolutions on top of it. We'll show using examples how that happens. Then we have something called pooling. Again, we'll talk about pooling in some of the later slides. So now notice one thing, that as we are going from the input to towards the right, one pattern that we are noticing is that these things are becoming smaller and smaller. Whatever these are, we'll look into that later. But these things, we are processing the image in some way, and these are becoming smaller and smaller. Which means what? That now from this was a huge structure, huge amount of pixels were there inside it. But now once we have gone from here to here, this has become much smaller now, so small that now it's kind of it has first of all, yeah. So we'll now have the resources to process this kind of data. So this is now some data dimension that is neither very big nor very low. So we can attach a fully connected layer here, and this fully connected layer will pass on to we'll use these fully connected layers to basically do our classification, assuming that we are trying to do a classification task. So that is kind of the pipeline of convolution neural networks. So now let's look in brief at the convolution operation. So it's like this, that you have an image in this way, in this form. Suppose it is what, 1, 2, 3, 4, 5, 6. It's a 6 cross 6 image. And then what will happen is you'll have weights like this. Okay, so these are basically again smaller grids of some 2D matrix of some size, say suppose 3 cross 3. Yeah. And now what we'll do is we'll take this collection of weights, these collection of these list of parameters, this matrix of parameters, and we'll convolve them over the image, right? So first we'll take this window, and then we'll take this window like we saw some classes back. So we'll go on convolving this particular weight matrix over the entire image. So now there are two I mean, what is the biggest advantage here? One is that obviously you have to, so let's talk about what happens after you convolve. So suppose you, as it's showing in the GIF, that you have this 2D matrix. You want to convolve this over the image. So your first window becomes this first 3 cross 3 patch in the image. So now when you convolve, basically you get one scalar value, and that sits in this first position because this was convolved with the first window. Then you move towards the right by one. Normally we'll talk about, suppose normally we move towards the right by one, and we take this second window that I'm pointing out. You again convolve here with this particular weight matrix, and you get the second value over here. Similarly, you convolve with the third window, and you put the third value. So if you follow the GIF, what how it's doing for some amount of time, you'll get it. Okay, I thought someone came. Yeah, so you'll get what this convolution operation is. It's very, very simple. So given an image, you'll have weights like this, which we call, which I basically, what I said, it's either called a kernel or a filter of weights. And what happens is once you pass this, convert this weight over all the windows in the image, what you get is this activation map. So this resultant output is called an activation map, which we saw here. So this is again called an activation map, which is the result of convolving this weight matrix with the image. So these are basically your neurons. So this neuron is what? This neuron is actually what this represents is that it's looking at basically this particular window in the image. Similarly, this neuron is looking at this second window in the image, and so on. And how you get these values, the values inside this is basically convolving this filter with the entire image. Note that this particular whatever is there in this filter, this is what we are going to learn. So the learning happens in the same way as we saw last week, or we have been seeing for a long time now in the classes also, that there'll be a loss function and there'll be back propagation. So that's how we learn the weights that are unknown to us. So the same thing is going to happen, just that the procedure is a little bit different. Normally, what we do is we connect in a normal neural network. We have this entire grid of pixels. We connect every part of this pixel to some weight vector, weight matrix or weight vector, to generate just one neuron. Instead of that, we are looking at a very, very local region. So we look at this particular window, and by convolving with the weight matrix, we get the value of the first neuron. So this is how the convolution operation happens. So now this probably will give you a little bit more intuition about what is happening. So these slides are taken from the course CS231N of Stanford. So what happens here? So what you have is a 32 cross 32 cross 3 image, right? And what we want to do is we want to have a neural network that preserves the spatial structure of the image. Because in order to have understand the meaning in the image, we cannot break it up into small pixels and then look at it. We have to have the all the objects intact in the image in order to understand it. So even the machine requires that, right? So this is like this width is 32, this length is 32, and then we have a channel of size 3. Now let's see what happens when we have a uh, uh, when we convolve something with it. So now suppose we have a filter, suppose like 5 cross 5 filter. So now in order to convolve this 5 cross 5 filter onto this 32 cross 32 matrix, since there's a channel dimension also, channel dimension 3, in order to process this channel, you also need a third dimension here. So it's a basically a 5 cross 5 cross 3 filter. So that this is how we are going to define filters in the image world when we have a RGB image of 3 channels or whatever channels. So what we would require is, if when we are defining a filter of learnable weight parameters, we'll always have this first two dimensions will basically define how big the kernel is or filter is, and this last dimension will basically correspond to how many channels you have in the input, right? So what it says here is, again, the warning is given here that filters always extend the full depth of the input volume. So it will be like this. So this 3 will be give, I mean, has to be used here as well to be so that the operation is meaningful. So now what we have to do is convolve the filter with the image, that is slide over the image spatially computing dot product. So very simple, as I showed in the GIF, you put it in the start putting it in the image in different parts of it and just slide through the image in order to and slide through the image, compute your convolutions and get the output values. That is all that is there. So again, to give you a little bit more intuition of what is happening, so suppose you have this filter and now you are convolving. So now you have, suppose you have taken this window inside the image and you are convolving the filter with the image values. What you will get at the end is just one number, right? So this is kind of what I mean. You have this 32 cross 32 cross 3 image, 5 cross 5 cross 3 filter, right? And this is what happens when you have one, I mean, so you have just what you get in the output is just one number. So this is what, so this is the result of taking a dot product between the filter and a small 5 cross 5 cross 3 chunk or window of the image. So now 5 cross 5 cross 3 means what? So it's basically 25 into 3 75. So because you are convolving this 75 dimensional weight matrix with the image, basically that means you have some 75 dimensional dot product and there's a bias term also associated. So this is what your briefly your convolution operation, one convolution operation basically on the image, which gives you back a number, right? So what you get is, at the end of this convolution operation you get something like this. So if you remember, maybe we talked about it this before also, or you can think of it from this point of view also, that when we convolve this with the 6 cross 6 image with a 3 cross 3 filter, what we get is a 4 cross 4 result, right? So always you will see that uh, most of the times the whatever input size you had given, the size always decreases. So that is how, I mean, I'll also show you how that happens, but for now just imagine that this, when you convolve this 32 cross 32 image with this 5 cross 5 filter, the resultant dimension that you get is 28 cross 28. And now because you are always getting one number from this convolution, what will happen is the third dimension will be 1 here, because you are getting just one number, not 3, not 5, not anything. That is why here we get a 1 on the depth axis basically. So this is just one filter, okay? So this is just one, fixed matrix of learnable weights. And now what we can have is, we can have a second filter as well, which will contain totally different weights. And we'll also want to learn them, right? And how many filters we'll have, that we can define from before. But this is, suppose this is another new filter, which is consisting of new weights, right? So once you convolve this filter with the entire image, you get another activation map. uh, which is of again 28 cross 28 cross 1. So now this was 128 cross 28 cross 1. This is the second one. So in total now you have two activation maps. Similarly, suppose we have six such 5 cross 5 filters. Okay. So that would mean what? That each of them gives us 28 cross 28 cross 1. So that is why if we stack all the 6 together, that will give us some 28 cross 28 cross 6 in the output dimension. Which means what? That this output dimension will always be equal to the number of filters that you are using. Okay. And I do not have the visualizations as of yet, but one thing that you can understand from here is that each of these 5 cross 5 cross 3 filters, why do we need different filters? So it's like in this image, if you convolve with different filters, so one filter, one set of weights might be suitable for catching the eye part. So those weights are only looking for eyes, right? There might be another set of weights, another filter, which might be looking for the nose. Similarly, there might be another set of filters which might be looking for something in the background. That is why we need to have different sets of filters that can basically capture different patterns in your image, right? So this is how your coordinate actually looks like, again in a nutshell. So you have a 32 cross 32 cross 3 in the input. So because of that you have a 5 cross 5 cross 3 filter. This 3 is because of this 3. So now suppose you want 6 filters to be there to learn 6 different things maybe. So now your output will be this 28 cross 28 cross 6 because you have 6 filters here. So now, because you have 6 filters here, in the next layer, what you will require is, suppose you again want to convolve, then what you will require is, this you can define by yourself, this 5 cross 5, 3 cross 3, 7 cross 7, anything. It should not be too big. Generally, people use 3 cross 3 or 5 cross 5 only. But this output dimension is defined here. So, because it's 6 here, your output dimension here will be 6 as well. But now in this particular network, people have used, I mean, in this diagram, they have used 10 such filters. That is why, because they have used 10 such filters, the output dimension in the next layer again becomes 10. And steadily this value starts decreasing. So from 32 we came to 28, then we came to 24 and so on. So this is how your convolution layers look like once you have them, stacked one after the other. So this is how your spatial dimensions keep decreasing as well. So one,
Ma'am, one quick question,
yeah,
please.
tell me.
How did you get 5 cross 6 in the second one? I'm confused there
Yeah,
because
yeah,
5
yeah,
cross 5 cross into channels, right?
yeah. So just look here. So this first one you have understood why we need three here.
Yes, ma'am.
Yeah. So the second one is very very similar. So you at this point you have a your input as far as your this layer is concerned. Your input is 28 cross 28 cross 6. Now if you do not have a 5 cross 5 cross 6 here, then how will you do convolution? You have to your basically your kernel should have the, I mean, whatever's in the x and y direction, whatever value it has to match this one for everything to work properly. So that is why you
Okay.
need a 6 here. So that is what I'm saying. Like whatever number of filters you choose to use in one layer, that becomes your channel width in the your channel dimension in the next layer. And in similarly, whatever filter you want to use in the corresponding next layer, you need these two to be same because you want to do convolution basically. And for smooth convolution operation, it's better that basically you are convolving in this way, in this x and y direction. That is why in order to match up with this z direction, you need this to match basically. So this 6
Okay.
and 6 should match. That's all.
Got it. Thank you. Yeah. So the first three was for the colors, and the next six is for the activation maps. Okay.
Right, right, right.
Okay. Thank you.
Yeah. Now, there are some other operations as well called strides. uh, one thing that we one thing that we didn't talk about before is called stride. So one, we always assumed, for example, take this gif, that it's always like moving one window at a time like this. So it will just shift from here, this particular window, to just the next particular window. So that is what we had assumed in the beginning, but it may not be so. So what we can do is, instead of, if we take this first window like this, instead of taking just the next immediate window, we just leave this one out. We take the window from here. So that is what is called stride, which means that once we take a window, how much step do I move in order to take the next window. So if the stride is 1, I just move from here to here to begin the new window. If the stride is 2, I move from here to here to take the next window. So that is what is meant by yeah. So that is what is meant by stride. So again, what I meant is that you have this particular window, and suppose this blue or green region is your kernel. So this becomes your first window. When your stride is 2, when your stride is 1, you just move by one cell. So this becomes your next window. This square becomes your next window. If you have a stride of 2, you leave this one, you go from here to direct here. Stride of 3 would mean you leave this one and you go from here to here. So that is all what is, that is what is meant by stride, right? And one thing that you can notice is, so it's there's a formula given over here. So what it does is, suppose you have given an input image dimension, and you have given the kernel dimension that you want to set along with the stride. It will directly give you what output size you want. For example, suppose you take this, what output size you'll get basically. For example, take this 7 cross 7 image, and suppose you have this 3 cross 3 kernel, and you have a stride of 1, which means what? We'll always move by one length only. So both towards the right, and when we go towards the bottom, then also we'll move by one only. So we have this stride here. So we have this window over here. So then we move towards this, then we move towards this, and so on. So now if you internally in your mind, if you calculate, you'll see that by going like this, are so basically what would that mean? If we go in this way, we can go ahead 5 by 5 steps. So this is one, this second is one, third is one, fourth is one, fifth is one, like this. So yeah, this will take some time for you to do it by yourself, but you'll see that if we move on like this in one step at a time, the output dimension is 5 cross 5. So that is what this formula helps you with. So suppose you have this stride equal to 1, then if your input size is 7, your kernel size I had defined to be 3. So this means 7 minus 3, which is 4, by the stride, which is equal to 1. So 7 minus 4 equal to 4. The 7 minus 3 equal to 4, by 1 is 4, plus 1 equal to 5. So this is nothing but a direct formula of how to, what would be your output size when you are given these quantities. But we are okay when stride equal to 1 and stride equal to 2. So when you have stride equal to 1, your output image size will be, your output activation map size will be 5. And for the other case, it will be 2, it will be 3. Problem arises when the stride is equal to 3. Why? Because try to imagine here, you have a window here, you have the first window here. Because stride is 3, you have to move to this particular window, right? So you have moved there, no problem. So now again, because stride is 3, you have to move here. Now from here there's nowhere to go, right? So that is why, that is intuitively why stride equal to 3 with this particular combination of image dimension and kernel dimension won't work. So here also in the formula it says that it's not an integer. So whenever it's not an integer, that would mean that this particular combination is not working out. So that is what it says, that it's not working out when stride equal to 3. And one, there are two ways to solve the problem. One is that you change this particular combination. Either you suppose change your kernel size, or generally you change your stride and so on. Or what you can do is you can do a zero padding. Zero padding means what? That you'll add something here in order to, basically you'll compensate for this particular thing. You'll add something on the around the image in such a way that this particular math works out, right? So it's something like this, that you have this original 7 cross 7 image, the one that is there in white. You add a layer of zeros around it, this box of zeros around it, and now that is that. I mean, how what has now happened? So my 7 cross 7 image has become 9 cross 9, right? And now this 9 cross 9, when I suppose, yeah, I try to fit it here. So 9 minus 3 equal to 6, by 3 equal to 2, plus 1 equal to 3. So here now we get an integer, which means that adding this particular layer of padding actually helps us, right? So the if you do such kind of a padding, suppose you add one layer of padding, right? So this is since we have just added, one row on the top or one row on the right, we say that the padding is basically, we have given one padding equal to one here, basically one pixel border. So yeah, that is a better way of explaining. So yeah, around the 7 cross 7 image, you have one pixel. It's like a border of one pixel around this entire image, which means what? Spatially, this contributes to two pixels basically. So one on this side, one on this side. Similarly, on the top, one on this side, one on this side. That is why your 7 cross 7 matrix has now changed into 9 cross 9. So all you have to do, a little bit modification would be required to this formula, where you'll have this. Suppose your padding, you define it to be a variable called p, and p was 1 for us. This one pixel border, as I talked about. So this formula will be n plus 2p minus f. So 2p means, because p was 1, 2p means 2. So n plus 2p, here 7, n equal to 7, 2p is 2. So 7 plus 2 is 9, and then f is again 3, and then you divide it by 3 and add a 1. So this formula is there in the next slide actually. So it's something like this, that so very quickly I'll go through it. Yeah. So suppose you have this kind of an image where your width is W1, height is H1, and depth is D1. So all your images need not be square. So because we can have rectangular images as well. That is why to accommodate that, we are having this sort of a image dimension. And now convolution, generally a convolution layer requires these four hyperparameters. One is how many filters do you want at every step, and then what is the dimension of the filter, which is given by this f, the stride amount, the number of steps that you want to cover before going into the next window, and the amount of zero padding p, right? So given these four things and the input dimensions, we can now calculate what would be the output dimension. So the output, suppose it's given by again a W2 cross H2 cross D2, this output, whatever activation map you are getting, and so these will be defined in the way that I just said. So it will be the original W1 plus 2p minus f by s plus 1. So this is exactly the formula that we saw in the last slide. Similarly, the value for H2 will be similar, just that instead of W1 you will have a H1 here, and there'll be a so we already know that your, as we saw in where did we go? Okay. Yeah, this one. So as we saw that your number of filters that you use always becomes the third dimension in your activation map. So that is why this D2 equal to K. This D2 means the channel dimension of your new activation map, and this becomes equal to the number of filters that you chose to use. Okay, somebody is, I mean, I can hear your audio. Can you please mute yourself? Okay, so now another thing that we noticed, yeah, another thing that we noticed is whenever we convolve like this, so yeah, so this particular kernel that we found, that we wanted to learn, this same kernel I'll move throughout this particular image. I'll convolve throughout this particular image, right? And that is why, so this phenomena is called parameter sharing, which means what? That we are sharing the parameters with different parts of the image. Okay, and now if you want to calculate, so this part actually shows you how to calculate the number of weights that you are introducing. So this is basically given by what? So your filter is generally a square matrix. So that is given by f cross f, and your in the first layer, since your channel dimension was d1, it has to be d1 here. So your kernel uh, yeah, kernel is of shape basically f cross d1, right? So that means what? Since it is so it's a matrix, right? So the total number of weights per filter would be f cross d1, right? And what you did was you wanted k of those filters, so each of these k filters will be different, they'll be learned separately. So that is why now your learnable parameters for the first layer becomes this f cross d1 into k, right? So there'll be these k weights, and also each of these so each of these neurons, each of these neurons will have a separate bias too. So that is why, yeah, as it's written here. So so you have k filters, so you'll have k biases as well. So you'll have these many amount of weights and these many biases. So I guess if you go through it in a little bit more detail, okay, yeah. And yeah, if you go through it by yourself, the math will become much more clearer. But yeah, this is an easy way of calculating how many parameters are there in the neural in the cnn's, how what is the dimension of output dimension of activation maps basically. So all those things you can take care of by yourself using these formulae. And so what does it say here? In the output volume, the dth depth slice of size W2 cross H2 is the result of performing a valid convolution of the dth filter over the input volume with a stride S. So this means what? That yeah, so any neuron, so suppose any neuron in this activation map is basically a result of the convolution of the first filter that you have with the image, okay? And similarly, when you have the second filter, a neuron inside this second filter, the second activation map, sorry, my bad. So a neuron inside this second activation map will be generated as a result of the convolution of your second filter with the image, and so on. So basically, if you take the fifth convolution, there are 6 here in this slide. So if you take the fifth activation map and you choose a neuron there, that is basically a result of your convolution of your fifth filter with the image basically. So that's all they are saying. And now let's quickly go through some a little.
I have a question.
Yeah, yeah, tell me.
So in the previous slide, if we take the, yeah,
uh,
previous to that.
okay.
So in any case, if we enter the bad parameters, like 7 is the
Hmm.
filter size and
Hmm.
3 is the 7 is the feature map size and 3 is the filter size,
Correct.
then what will happen in the case of coding? Like if we enter a slide of 3, then
Yeah,
we know that
yeah.
it's 2.3.
It'll give an error. It'll throw an error. So if you want to code up convolution neural networks anytime by yourself, you should throw an error. So this should be a check for you that this thing should come up to be an integer, because otherwise the entire so just go through it by yourself when I upload the slides. So
Mhm.
just keep the input to be 7 and this the kernel's shape to be 3, and keep a stride of 3. You'll see that the convolution operation is not happening properly. So that is why you
Hmm.
cannot allow something like that. So you have to throw an
So
error.
there was a question in the assignment which asked for the output dimensions of the image,
Hmm.
and this turns out that the number comes out to be a decimal,
Okay.
and it still asks for the output size. So
Right.
that
So
is
yeah, so whatever you understand from this slide, I can't tell you the answer, but whatever you understood from this slide, you have to answer that. So
okay.
the concept is that based on your given image size and this f, you have to be able to do the convolution operation. Unless you are able to do it, that's an error.
Okay.
So that's yeah. So just a little bit more detail. So we talked about this pooling layer. So
Ma'am, sorry to interrupt. I
yeah,
had a question.
yeah, please go on.
So we are nearing towards the end of the hour.
Hmm.
So I thought this is not on convolution. This is on the SE squeeze and excitation on the ResNet.
Hmm.
So I was trying to implement one portion of it, but it's though I'm able to understand it, getting it implemented is a little challenging. So would you have any sample implementation of the bottleneck, the squeeze?
Yeah.
If you
First
can
of
share that,
all,
yeah.
yeah, so see, first of all, resonets and all. So the best trick is that you just go to Google and type resonate architecture, PyTorch or anything. That is the
Right.
best thing. And yeah, I'll also these code also will share. So
Yeah,
there
if
also
you
you'll find,
can, if you
yeah,
have some 2-3 minutes towards the end, you
yeah.
can explain that bottleneck with the code.
Bottleneck, yeah, even I'm not very sure of it at this point, because see, these things are very difficult to remember. So maybe I'll go through it next
Maybe if you
time and
can share a sample code in
yeah.
PyTorch,
Sample
I
code
will
will be there.
see how it gets. Because what
Yeah.
happens is there is a lot of mismatch between the matrix
Correct,
sizes and
correct,
all
correct.
that
I
happens when
understand.
I
Yeah.
implement. That's
So
why,
code
yeah.
snippet is already there with us, and also in these kind of architectures like ResNet, VGG, etc., you'll have, I mean, thousands of implementations on net. Not
Right, right.
thousands, there'll be one implementation only, but there'll be thousands of links that contain that those implementations. So you can take them up anytime. So and we also have the same snippet. So it's always the same thing. Anyway, so yeah, that will be shared with you. And yeah,
So you will share it in the this one, the chat, or you will send a.
wait. Let me do that right away.
Yeah. I did go through the internet, the Google thing, but
Hmm.
then what happens is the way some people have implemented is still, there is a lot of confusion there. So,
Okay. Yeah, go through this one. Probably it'll just let me know. Let us know if you have some doubts on this.
okay.
Yeah. So very quickly, let's go through pooling and max pooling and average pooling.
Uh,
So
ma'am, just one small doubt.
yeah.
Uh, why everybody in the deep learning is using only the square kernels? But why nobody is using the rectangle kernel?
Because yeah, this is a convention, you can say, because this yeah, in the square way you are doing the convolution. So see, some choices we do not have answers to. It's just that
Any
people.
specific reason of not choosing rectangle, or it is just like everybody is using, so everybody is using square?
I'll have to think of that. That's a very good, interesting question. Actually, I'll have to think of why people use these square things. So. mm Again, I mean, probably one reason is that it's much easier to process when you have a square sort of an architecture. So it, if you suppose have a 5 cross 6 here, it only makes your computation difficult, your output calculation difficult, like what would be the output size and all. So that is why people generally, when they look at images, they look at it in the from the perspective of a square patch. So image is like treated as a patch of I mean collection of patches which are square in size, because squares are easier to process. You can think of it in that way. So again, if you convert it to 5 cross 6, it becomes just a bit more complicated. So that is the reason I can think of upfront. If I come up with anything else, I'll let you know.
What about the processing by GPUs and computational side?
uh,
Will it make faster with square calculations and everything?
that might be, that's a good possibility. Yeah, probably. Yeah, again, that's what I'm saying, like processing ease, people take these to be squares. So again, processing ease means, obviously from our part that is true, from the coding point of view that is true, and obviously from the GPUs and whatever machines you are using to compute these things, you have to make the process easier for them. It's better to use square matrices for the kernels. yeah, if I come up with something more interesting, I'll tell you. But yeah, now I have to proceed quickly because we have I mean, a lot of time has passed. So yeah, let's look at pooling. So pooling is again a very vital operation that is a part of neural networks. So it's a downsampling. So this is basically a downsampling operation. So again, downsampling means what? That whatever activation map you had got, this basically I mean, that activation map itself is a smaller version of the image, but now you are again downsampling it again in I mean, downsampling it further, right? And what you are doing here, let's just go through the operation only. So suppose you have, what you do is, suppose you have a you have to define a hyperparameter here, pooling, how much pooling you want to do. Suppose you want to do a 2 cross 2 pooling. So what you'll do is you'll go through this image in terms of windows of size 2 cross 2, right? And suppose you take this 2 cross 2 grid here in the image. There's no kernel involved now, but what you'll do is in this grid, you'll find out what is the maximum value. So this is called max pooling. So in this grid, what is the maximum value? You take that and you put that somewhere, you store it. Then again you go to the next window, and again you all window sizes will be 2 cross 2. So again you go to the next window, and again you pick out, you know, the maximum value here, and so on. So that means what? That you are downsampling the image. You are retaining probably the max values, basically refer to like where your new, I mean, the, because this is a kind of a collection of neurons, it's a matrix of neurons. High values means where, you know, your weight parameter and the input image, the I mean, that interaction between the weight parameters and the input image, they led to some high value. So that is what the high values kind of account for. So what you are doing is, you are in effect, you are in some sense storing those high values. You are losing some information, but because you are storing the high values, it's preserving the aggregate information that you had collected till now through your neural network. And yeah, that is you know, converted to this. So at the as a result of this particular operation, you'll get a smaller downsampled matrix like this, which is smaller than the original size of the activation map. So a similar operation is called average pooling, where what you do is, instead of max, you simply do the average. So again, why you do, when you want to do max, when you want to do average, those things are again very application specific. This is entirely up to you. Many people use max pooling, but nowadays this average pooling is also gaining a lot of ground. So now what you have done is, at the end of this pooling layer, you see that now you had started with something very big. So after many convolution layers, pooling layers and all, suppose you have come up with a smaller version of the image. So a smaller version of the activation map is basically, which you can now flatten into an array, and now you can handle it using the original neural network architecture that we saw in the last week. And this is basically, which means that you can flatten it and pass it on to a fully connected network, which will finally give you the classes. So that is what the FCs are about. So now this particular layer of neurons, they basically have captured all the aggregate information that was there in your image, and now they can be sent to the fully connected neural network in order to be your final classification. So this is the last slide. So this is a typical neural network that is there. You have a car image, and it starts with so it has many convolution layers followed by ReLU layers and so on. Some pooling layers will be there and so on. So this will continue until you have generated some smaller dimension of your entire image, smaller representation of your entire image. And once you have done that, all you have to do is flatten that into a vector as I showed, and then pass it on to a fully connected layer to generate, predictions like this. So this is what a typical neural network looks like. So very quickly, so we are already I talked a lot today. So yeah, I'll very quickly go through the code once, so that yeah, so this is what I wanted to show you with the ResNet architecture. So I, before starting the class, I actually ran the code. So whoever asked about ResNet, so this code works fine basically. So yeah, I mean, I already shared the link with you. So okay, why isn't it scrolling very okay, let's yeah. So this particular code notebook that I've shared with you, this basically deals with some data set called CFAR 10. So this CFAR 10 data set means that it has a collection of images, and it's like each image is attached with a label as it always is, and there can be 10 such labels. So that is why the 10 is there in CFAR 10. Okay, so no, okay, my bad. This one again deals with the MNIST data set. So MNIST is again, as I reminded, as we went through last time, it's the handwritten, digits data set where the digits start from 0 to 9. So this is kind of, how PyTorch code looks like. So you have to, these things you can learn only by playing around with it. So go through the code base. So all these import functions you have to do. So PyTorch, what you have to do is you have to convert the data using data loaders and all in order to get batches of images and corresponding labels. So that is given by this this functionality called the data loader and data loading basically. So yeah, let's not look into these things. Yeah, so the train model very quickly. So this block of code basically trains your model. So what you do here is that you have to basically in your neural network you have to run your code for so you have to train your model for a certain number of epochs. So epochs means basically these are iterations you can understand from the code. So num epochs is basically some hyperparameter that you defined from before, and then what you do is your data loader, if you again go through the code you'll get it. So the data loader gives you your images and labels in the form of batches. So batch size you can define somewhere above, and yeah, so basically what it does is this features comma targets means this is some raw image, and this is the some batch of raw images, and this is a batch of target labels. So what you have to do is, because you are operating in GPUs, you have to do this operation first in order to, so that these tensors can be, these are basically called tensors in the PyTorch language. So you have to make sure that these tensors can be, operated in the GPU as well. So this piece of code is required for that. And then what you do is your model is predefined. So you pass your features, which are the raw images basically, you pass them to the model, and what you get on the output is called logits. So this is the model output is basically called logits. So this logits is basically what you pass through the cross entropy loss as is defined here. So all the functionalities are given by PyTorch already. So you pass this logits along with the, so this is basically the predicted value and this is basically the true value. You pass them on to the loss function, and you do a back propagation, and here basically you are printing some statistics. But yeah, where are we on this one? Let's scroll down a little bit. Yeah, so yeah, so this is the model part, this is the most interesting part. So if you want, this is, if you want to know, this is basically the code for the ResNet blocks. So this is, I think, ResNet 34 or something is defined over here. So yeah, these, all these operations, these are all convolution operations that PyTorch has already implemented. So in planes actually stands for your channel dimension, and out planes stand for the number of filters that you want. Again, as I say, if you have any confusion here, for example, before this class I was unable to recall what this in planes and out planes can be. So all you have to do is just go to Google and type this thing. So PyTorch has very very good documentations of everything. So all these parameters that you have to send, all these are very well defined uh, in the documentation. So yeah, so this is the basic block that is defined for ResNet. So again, I mean, I do not need to go into them because these are all defined by the ResNet architecture. So those of you who do not know, ResNet is a a very deep neural network, a convolutional neural network that is being trained on images for classification and other tasks. So the architecture is predefined here. So if you do not know about it, just go through it. There's a research paper also available. So yeah, this is the bottleneck class basically. So it's already defined out here, and yeah, the ResNet class. So this ResNet class basically, this class defines your final ResNet model, which is built of these basic blocks and bottleneck and other things. So yeah, I spent so much time today in the CNN part that I should have actually spent more time here, but yeah, we are already way past our time. But yeah, I mean, I guess you saw some of it in the previous lectures also. So but just go through it, run it. So the training happens basically here. So you can see that so it's like epoch 1, you can see the loss is decreasing steadily from here to here and so on. So yeah, I mean, just go through it. I think you'll have a better understanding of what's going on. So I'm extremely sorry for going through this in such a rush, but yeah, we'll have to end now. Fine, guys, we'll meet next week then.
Thank you.
Thank you.